Okay, we welcome you to this lecture. Today we last time, if we go back, we discussed this quiz 2.7. Now today we are discussing last few topics of this chapter, and we start discussing 2.8, that is variance and standard deviation. So standard deviation and variation. So I told you that in probability we just want to evaluate or analyze our random variable. So one way of analysis is looking at the PMF, and other is looking at the CDF. After that, the point from where we can comment on any random variable, we use the expected value. Now there's another properties that we can use. So it's first one is the variance. So if we look at the definition, is 2.16. So this is variance. Now variance, the variance of random variable axis, variance of x, that is equal to expected value of x minus mu of x whole square. So this is called the variance. Then there's another one, that is standard deviation. Standard deviation. Now the standard deviation of a random variable x is written as sigma of x is equal to under root variance of x. So this is the way we can calculate the standard deviation and variance of a random variable. Now it is useful to take the square root of variance, because standard deviation has the same unit. For example, you have exam point as x, the unit of the variance are square of the units of the random variable. So thus standard deviation can be compared directly with the expected value. Okay. Now we think of a sample value within standard deviation of the expected value as a typical value of x, and other values as unusual. So normally when x belongs to expected value minus standard deviation and expected value plus standard deviation, so the range of values of x is known as typical values. So this is very important. If your mean is the central point, if you go on the left side or right side of the one standard deviation, so the values of x is known as actually the typical values of x, values of random variable x. So the other values are also remaining, is called unusual values. If it is away from the 1 unit standard deviation. So these are also measures that will help us to analyze the random variable. So we can say that variance of a random variable x is actually equal to square of standard deviation, or we can write it as a summation x minus mu of x whole square times p x of x. So there's a theorem is 2.13. So it says that the variance of a random variable is actually equal to expectation or expected value of x square of random variable minus square of their expected value, or we can write it as expected value of x square minus square of expected value. So this is the way you can calculate the variance. Now there is another definition. Definition is 2.18, and this definition about moments. Now moments for random variable x. Now the nth moment is calculated at expectation of x, nth expectation. So similarly the nth central moment is expectation of x minus mean value over n. So this is central nth moment. Now let's consider an example here. Then move to next page for example. So example is 2.34. So this example says that we have PMF given to us, that is 1 by 4, 3 by 4 and 0. 1 by 4 when r equal to 0, r equal to 2, otherwise. Now this is the PMF, and we already calculate the expected value of this PMF in previous example is mu r, that is equal to 3 by 2. Now question is, what is variance of r? Now we know that how to calculate the variance. So variance by definition is equal to, if we apply the theorem 2.13, is equal to expected value r square minus mu r square. Okay. Now this is the way you can calculate the variance. Now there are different ways of calculating this variance. Now this is the one method. There's another one that says that variance of x is equal to expected value of x minus, okay, let me write it again. Okay. Second one is written as variance of r is equal to expected value of r minus mu r whole square and then take the expected value. So this is the second method. Now let's see how we can solve it. So assume that we have a W that is equal to R minus mu R square. So that come out to be R minus 3 by 2 whole square. Okay. So this is your W. Now let's write the PMF of W. So PMF of W is equal to 1 by 4 when W is equal to 9 by 4. Similarly, it becomes 3 by 4 when W is equal to 1 by 4, 0 otherwise. So how we calculate this? We know that R is 0. When we put in this equation, so W becomes 0 minus 3 by 2 whole square, that becomes 9 by 4. Similarly, when R equal to 2, we put in this formula, W becomes 2 minus 3 by 2 whole square, and it becomes 1 by 4. So this is the way we can calculate this PMF. So after calculating the PMF, so variance from formula number 2 is equal to expected value of R minus mu R whole square. R is equal to expected value of W. So we know that what is the expected value of W. So it is 1 by 4 times 9 by 4 plus 3 by 4 times 1 by 4. So if we solve it, it becomes when we calculate it, so it becomes 3 by 4. So this is the one method. So this is one method that we can solve it. Now we move to the next method. So for next method, method number 2, so we know that variance of R is equal to expected value of R minus mu R whole square. Now if we use the theorem that is 2.10, so that says that this expected value actually equal to R belongs to SR. So if you remember, that is R minus mu R whole square P of R of R. So we did discuss, this is from theorem. If you just go to theorem 2.10, this will tell you how to do it. Now we plug in the values, so it becomes when R is there are two values for R is 0 and 1, so it becomes 0 minus 3 by 2 whole square P R of 0 plus plug in the second value, that is 2 minus 3 by 2 whole square P R of 2. So when you plug in the values, so it becomes 3 by 4. Again the same result. Now the third method, that is using theorem 2.13, that says that variance of R is actually equal to expected value of R square minus expected value of R whole square. So we already know that expected value of R is equal to 3 by 2. Now we have to calculate expected value of R square. So it becomes again our expected value of R square, so it becomes R belongs to SR, R square P R of R. So when you put in the values, you have 0 square times P R of 0 plus you have 2 square times p r of 2. So when you plug in the value, so it becomes 0 plus 4 times, so pr of 2 is 3 by 4, so 4 times 3 by 4, so it becomes 3. Okay. Now put in the formula. Formula says variance of r is equal to expected value of r square minus expected r whole square. So when we plug in the values, it becomes minus 3. So mu is we already know 3 by 2 whole square. So when we solve this, this again becomes 3 by 4. So look here, there are 3 methods of solving calculating the variance. So first method was you make a drive random variable and calculate the PMF and then calculate the expected value. Okay, that becomes the variance. Second is directly calculate it using the theorem 2.10, and third is using the theorem 2.13. Now move to next thing is theorem 2.14, and it says that if you have a variance of ax plus b, so they don't follow the linear combination, which is equal to a square of variance of x. So let me do an example here quickly. This is example 2.35, and example says that a new fax machine automatically transmits an initial cover page that produces the regular fax transmission of X information. Using this new machine, the number of pages in a fax machine is y is equal to x plus 1. Okay. Now what are the expected value and variance of y? So we have to calculate expected value of y, and also we have to calculate the variance of y. Now if we try to solve this equation, so we know that expected value of y is equal to expected value of x plus 1. So if we apply the theorem on expectation, it becomes expected value of x plus 1. Okay. Now if we want to calculate the variance, so variance of y is equal to the variance of x plus 1. So we applied this theorem, that is theorem 2.14, so it becomes variance of x. Now let's look another example, that is 2.36, and it says that PMF given to us of the voltage, that is 1 by 7 and 0 otherwise. 1 by 7 when V is minus 3, minus 2 up to 3. Okay. Now so he says that a new voltmeter records the amplitude U in millivolt. So millivolt means that 1 U is equal to 1000 of volts. So this is the function. Now he is asking what is variance of U we have to find. Now first of all calculate the expected value of V. So expected value of V is as we know that mu of V, that is equal to summation belong to S of V, V times P capital V of small v. So when we do that, it becomes 1 by 7 times minus 3 minus 2 minus 1 plus 0 plus 1 plus 2 plus 3. Okay. So when we do that, it becomes 0 volt. So it is obvious because this is a sinusoidal wave and mean value is 0 because we have same number of. Now the next thing we have to do is, so we know that expected value of v, which is mu of v, is equal to 0. Now we have to calculate expected value of v square for calculating the variance. So for v square, same thing. Now we have minus 3 whole square plus minus 2 whole square plus minus 1 whole square plus 0 square plus 1 square plus 2 square plus 3 square. So expected value of v square becomes 4 volts square. Now variance of v is equal to expected value of v square minus expected value of v whole square. So plug in the values, it becomes so it becomes 4 minus 0 square, that becomes 4. Now we have to, we know that u is equal to 1000 v. Now we have to calculate the variance of u. Now if we apply the formula, that's equal to variance of 1000 of v, that becomes 10,000 square time variance of v. When we plug in the values, so it becomes because this is 4, so variance of u becomes 1 2 3 4 5 6 6 millivolts. So this is the answer that we can get after applying the theorem. Now we have theorems 2.15. So this theorem tells us, the first one, if x is Bernoulli, p, then variance of x is equal to p times 1 minus p. Second one is, if x is geometric p, then variance of x in case of geometric becomes 1 minus p divided by p square. So the third one is, if x is binomial, that n comma p, then variance of x is equal to np times 1 minus p. Now d is if x is Pascal, then variance of x is equal to k times 1 minus p divided by p square. Now the e is, if x is Poisson, so in Poisson we have alpha, then variance of x equal to alpha, and we have last one, if x is discrete uniform, that is k of, then variance of x is equal to L minus k times L minus k plus 2 divided by 12. So this theorem tells us how variance look like for different random variables. Now we move to a quiz here. 2.8. The quiz says that in an experiment to monitor two calls. Now the PMF of n, the number of voice calls is, so this is given to us that we have 0.1 when n equal to 0, and then we have 0.4, then we have 0.5, then we have 0. Now here n is 1, here n is 2, and here is otherwise. So this is given to us. Now question is find. Now we have to find, question is to find the expected value. First one is expected value of n. Second one is second moment on, that is n square. Third one is variance. Expected value is also known as first moment of. So this is second moment of with square. Now the variance of n, and then the standard deviation. The last one is the standard deviation of n. So now let's look at the solution. So expected value of n, first one, expected value of n, and just put the formula, that is summation, and belongs to s of n times the n of n. So just plug in the value 0 times 0.1 plus 1 times 0.4 plus 2 times 0.5. So when you do the calculation, it's come up to be 1.4. Now we will move to next one. The next question is expected value of n square. So again, if we look at the formula, so only difference is we have to take the square this time. So this is n square here. So in that case it becomes 0 square times 0.1 plus 1 square times 0.4 plus 2 square times 0.5. So this is 0 again, so this is again 0.4, this is 4, this becomes 2. So in that case this becomes 2.4. Now now the third one is the variance and standard deviation. So I wrote here the third one is variance of n. So we know that it is equal to expected value of n square, then minus sign the expected value square. We already calculated these two, so variance of n becomes 2.4 minus 1.4 square. When we solve this, this becomes 0.44. Now the fourth one is the standard deviation of n, and we know that this is equal to under root of variance of n. That becomes under root of 0.44, so which is equal to 0.663. So here we conclude this article 2.8. Now we move to next article, which is last of this chapter, is 2.9, that is conditional probability mass function. So this is the last one. Now for this, if we look at the definition 2.19, and this tells us the conditional PMF. What is conditional PMF? So if given the event B with probability of P is greater than 0, the conditional PMF of random variable x is written as, this is PMF. For conditional we have to put a straight line and with B, which is the condition of x. This is known as conditional PMF is equal to probability of capital X similarly is equal to x such that P. So we have to write the conditional probability of each x, so that we call it as conditional PMF. Now we look at the theorem that help us to solve these problems related to it. So this is theorem 2.6. It says that a random variable x resulting from an experiment So what is experiment with event? With event space, we have event space that is P1 up to, let's say, Bm events as PMF. So if we want to calculate the PMF of x with event space, this is actually equal to summation I is from 1 to n conditional PMF BFI of x times probability of yeah. So this will give me the original PMF of the system. Now let's look at the theorem here. So theorem is 2.17, and theorem says that conditional PMF can be written as, if we know the PMF, if we divide by the probability of P for all x belongs to B, so this gives us the conditional behavior. So this will make our life more easier. Now example, let's do an example. Example is 2.39. Example says that we have PMF of x given to us. So these are 0.15, 0.1 and 0. So x is 1, 2, 3, 4 and x equal to 5, 6, 7 and 8, 0 otherwise. Now question is, suppose the company has two fax machines, one for fax shorter than 5 pages and other for fax that have 5 or more pages. What is the PMF of fax length in the second machine? So so we have to find the PMF for second machine that has 5 or larger. So is that if I say L belongs to 5 or so it has 5, 6, 7, 8. Now we have to find the PMF given F that is equal to PMF of x divided by probability of L. So this is for 5, 6, 7 and 8, 0 otherwise. Now for this we have to calculate probability of L, that is equal to x from 5 to 8 PMF of x. When we solve this come out to be 0.4. Now when we plug into this one, so PMF of x given L is equal to 0.1 divided by 0.4, okay, 0, so say x equal to 5, 6, 7, 8, 0 otherwise. So this is the way you can calculate the conditional PMF. Now if we move to next one, here question is now let's do another theorem, and theorem is 2.18, and theorem says that for any x belongs to event B, PMF of x, conditional PMF is always greater than or equal to 0. Similarly, so this is from axioms of probability. Similarly, if I x belongs to B and if I calculate all the conditional, the sum must be equal to 1. So last one is that for any event C, which is a subset of B, probability of C given B, the conditional probability that x is in the set C is probability of x given B of x. So this is the way we can calculate the conditional probability. Now for conditional probability, then we have another definition here. It's 2.20 and it is about conditional expected value. Now conditional expected value of a random variable is written as x condition B is actually mu x of B, that is given same that x belongs to B, x probability of B of x. So the main idea is expected value is basically with the PMF. If PMF is conditional, that this is a conditional expected value. Now there's another theorem, that is 2.19, and theorem says that for a random variable x resulting from an experiment, okay, with event space event space is B1 up to Bm, expected value of x equal to summation i's from 1 to m, expected value of x conditional expected value times the probability. So this is actually, if B is event space, then this is true, okay, we know that. Now the theorem 20. So this is all extension from the basic theorems that we have about random variables. And theorem 20 says that the conditional expected value conditional expected value of y, that is equal to g of x, given condition B is. Now here conditional is basically with the B. Now in that case, expected value of y given B is equal to expected value of g of x. So as we know that given B, which is equal to summation x belongs to event B, g of x, and p x of B of x. So this is the way we can calculate the conditional expected value. Now